Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back. Today we are talking about a new topic, Unit 7.1, Momentum. Okay? All right. Let's get on with it. Okay, so what is momentum? So basically, let's start from the very start. Momentum is a vector quantity. Okay, that's the first thing you need to know. Um, it is defined as the mass multiplied by the velocity. Let's read through this and then I'll explain it a little bit more. A moving object has two main characteristics, its mass and its velocity. In this lesson, you'll learn how mass and velocity combine to yield a new physical quantity of great importance. So it is a physical quantity. That's the first thing I want you to know. Moving objects have momentum. Okay, so it must be moving. An object, in order for an object to have momentum, it must be moving. Imagine standing on a skateboard while a friend tosses a heavy, slow-moving ball at you or to you. Catching the ball causes you and the skateboard to move with a certain speed. If instead your friend throws a lightweight but fast-moving ball, the net result can be the same, as indicated in Figure 7.1. How is it that a fast, light-moving ball can have the same effect as a slow-moving heavy ball? Okay, so this is momentum. Momentum is basically the amount of oomph, the amount of almost like energy that something has. So I want you to imagine a scenario where um, basically like a truck that's moving really slowly uh, hits a pedestrian. That can cause a fatal injury. The same way a small tiny bullet moving really, really fast can cause a fatal injury. Both of those things can have the same energy. And in fact, they can have the same momentum, even though they have different masses. How come? Well, one of them is a lot bigger than the other, even though it's not moving as fast. So we think of bullets as being deadly because they carry a lot of energy, um, but they also carry a lot of momentum, right? And these two things are related. Um, Even though we didn't get a chance to actually cover energy. So if we're talking about kinetic energy, for example, that's half times mv squared, right? Momentum, okay, this is what we're talking about today. Momentum equals mass times velocity, okay? So you can see the similarities between the two. Both of them have mass and velocity. This one has mass and velocity as well. I should write the formula actually for momentum. The formula for momentum is P equals m times v. So you can see the shared links between the two. So when I said it's like energy, not exactly, but you can use that analogy. So a small bullet traveling really, really fast can have a lot of momentum, a lot of energy. And a big, big truck traveling really slow can also have a lot of energy because it has a lot of mass. And of course, objects that have big mass and big velocity have a lot of momentum. Okay? So the example they used over here is basically two different size balls. So you see here, that's a big ball. Oh, sorry, I'll use a different color because I'm colorblind and it's really hard to see those colors, like yellow on, sorry, green on peach or whatever. Here we go, big, and that is small. And as you can see, even though that's big, this over here is big, and that is small, the person is traveling at the same speed. Let's give him some speed. So 2 meters per second, and here is traveling at 2 meters per second. So how come? It's because these balls, both of these balls have the same momentum. Okay? Both of these balls have the same momentum, even though they have different masses. So why is that? Because this one must be traveling slower. So it's a bigger mass, but it's traveling slower. This one is a smaller mass, but it must be traveling faster, causing this person here to have the same velocity. Anyway, what I want you to take away from this slide is that momentum is a physical quantity. It is a vector quantity. It has a magnitude and a direction, and it is related to energy. It is related to energy. Momentum has a formula. It is mass times velocity. In order for an object to have momentum, it must have velocity. Well, how come? Because look, P equals m times v. If v is 0, then of course there's no momentum. Okay? So in order for an object to have momentum, it must have velocity. What are the units for momentum? Well, I don't remember the unit for momentum. Well, I do, but let's say, for example, I don't remember the units for momentum. Then I know the unit for mass is kg. I know the unit for velocity is meters per second. And that there is multiplication. That's exactly the unit for momentum, kg dot meters per second, right there. Okay, let's move on. Okay, so here's an example. A 1,200 kilogram car is driven through a town with a speed of 15 meters per second. What is the magnitude of the car's momentum? Honestly, this is like one of the easiest lessons, guys. So what do we have to do? Momentum equals mass times velocity. Do we have the mass? Here's the mass. Do we have the velocity? Here's the velocity. Straightforward multiplication. Okay, so 1,200 multiplied by 15, which last time I checked was 18,000 kilograms dot meters per second. Okay, and that's how you do that one. Okay, hopefully nothing too hard so far. Righto, let's do some questions. What I'd like you to do, as always, is I'd like you to try and figure these questions out. So pause the video, do the questions, and then check with me, check the answers. Give yourself 2 or 3 minutes to finish answering these before you check the answers. All right, I'm going to go ahead anyway. So question one, a major league pitcher can give a 0.142 kilogram baseball a speed of 45.1 meters per second. Find the magnitude of the baseball's momentum. So, what do we do here? Let's have a look. Question one. Um, Once again, that's the formula. Okay, in fact, I'm just going to beautify that by highlighting it because that's really all you need to know. I mean, honestly. Here we go. Nice and rectangular. Okay, so let's go back to pen and let's go to this color here. So what do we have? We have the mass and we have the velocity, speed in this case, because it doesn't really tell us the direction, but that's okay. So mass times the speed, mass times the velocity. So 0.42 multiplied by 0.42 multiplied by 45.1, and that is equal. So I'm just going to do the workout as well. 0.142 P equals mv, which is 0.42 times 45.1. So that is going to equal 6.40 because we've gone to three significant figures. Kilograms dot meters per second. That's the answer. Question two. Question two says the momentum of a 12 kilogram dog racing to greet its owner has a magnitude of 37 kilograms meters per second. What is the dog's speed? What is the dog's speed? Okay, the dog's speed is This is where the triangle comes in handy. In order to calculate the speed, it's going to be P divided by M. Okay, so it's always good practice to write that first. That's the mass, that's the momentum this time. Do I have both of them? Yes, I do. So it's going to equal 37 divided by 12, which is something like, oh, two significant figures. So it's something like 3.1 meters per second. Okay, that's the answer. Let's go to the third one here. Rank. The masses and speeds of four objects are given in the following table. Rank the objects in order of increasing magnitude of the momentum. Increasing magnitude of their momentum, sorry. Indicate ties where appropriate. Okay, let's have a look. So they want the lowest momentum first and the highest momentum last. So what do we have? Mass and speed. So mass and velocity, essentially. I'm just going to do one more thing here. I'm going to be cheeky, and I'm going to add one more column, one more row, sorry, and five more columns. So I'm going to write momentum in this one. 10 times 10, 100. 15 times 4, 60. 5 times 10, 20, 100 again. And 60 times 3 is 180. So the order is going to be B, A, and C, D. And since they say highlight the connection, indicate the ties were appropriate, here's an obvious one where A, even though A has double the mass of object C, you can see that, double the mass, it has half the velocity, and therefore overall has the same momentum. What that means, I want you to think about it this way, like if somebody punches you, um, and let's say their arm, their fist, and their arm, generally speaking, weighs about 10 kilograms, and they punch you with a speed of 10 meters per second. That's going to cause you the same pain as somebody smaller, perhaps somebody with a 5 kilogram arm and fist combo, punching you twice as fast. That's what it means. Okay? That's essentially what momentum is. Okay, let's move on. Vectors for momentum and velocity are related. Of course, they are related. So, in short, I'm just going to read this and then I'm going to summarize it once again. In many situations, only the magnitude of the momentum is of interest. The direction doesn't really matter. Um, in other cases, the direction of the momentum plays a key role. But what is the direction of the momentum? From the definition, P equals mass times velocity, it follows that the momentum vector points in the same direction as the velocity. Of course it does, because mass doesn't have a direction. It's a scalar, it's a constant, it's a non-quantity. If the velocity changes direction, the momentum changes direction as well. Okay, that's a given. That's what you need to know there. So both momentum and velocity have the same direction, have the same direction. Great. Um, I'm bored of this color. We're going to go to red. Analyzing the beanbag experiment. So now we're going to come to a new concept, which is that momentum It can be calculated across the system. And what that means we'll come to find out. So sometimes the question will ask what is the total momentum, and what it means by that is you got to calculate the total momentum of all the objects and then find out the net momentum. So you know how we talked about net forces? You've got 2 newtons acting from the left, 2 newtons acting from the right, and then the net force would be 0. Well, momentum follows that system, right? In this case, in this instance, what they want to show you is that the direction matters. So here we have two objects. We have a teddy bear and we have a ball. Now, they're both the same mass, 1 kilogram each, 1 kg, and that's 1 kg as well. The only difference is that the ball is bouncy while the teddy bear is not. So what happens? So basically, the teddy bear would fall down, and it's full of like those rice beads or whatever. So it falls down and it doesn't bounce back up. It stays there. What happens to the ball? No, the ball bounces back up. So what is the momentum? They want to calculate the momentum of the beanbag and calculate the momentum of the rubber ball. What I'm going to do is I'm going to calculate the momentum of the beanbag, or just explain what they've done here. The final momentum of the beanbag, the change in momentum, if you want to calculate the change in momentum, which is what they've asked for, they want the change of momentum. To calculate the change of momentum, and of course you remember triangle means change. This means change in velocity. This means change in time. This means change in speed. This means change in acceleration. That's all it means. The triangle just means change, which means final velocity minus initial velocity, final momentum minus initial momentum. That's all it means. Right. So we've got the change in momentum equals final momentum minus the initial momentum. What is the final momentum for the beanbag? They've got 0. Why do they have 0? Okay, because final momentum equals the weight, the mass, sorry, 1 kilogram multiplied by 0. Why? That's velocity. It's not moving. Look at it. It's happy without moving. So there you go. So of course that's 0. But before that, the initial momentum, it was moving. Here we go. See, it was moving towards towards the ground. What was the speed then? It was -4. -4 meters per second. Why negative? Remember, velocity matters. The direction matters. So because it's going down, we're going to assume that down is negative. It doesn't matter if you assume it's positive as long as you assume that the upward is negative, right? So anyway, final momentum is 0, but initial momentum is going to be minus 4. And so it's going to be 4 kilograms meters per second upwards. Okay, why upwards? Because that indicates downwards. So overall, it was 0 minus minus, so it came upwards. Let's look at the rubber ball. What happened to the rubber ball? The rubber ball has a final momentum of 4 kilograms meters per second. Why? Of course, the initial momentum we know is going to be the same as the bear. That's not a problem. We know where that came from. That's the same as that. It's going down. Here it is. It's going down. Same as this. Same mass. No problem. But where did this come from? Where did this guy come from? Well, it bounced back up. Look, it bounced back up. What was the speed? Obviously, it was 4 meters per second. How do I know that? Because over here, it was -4. And they said that the momentum was exactly the same, just opposite. So must have been 4. 4 meters per second up. 1 kilogram is the mass. Momentum equals, so the final momentum for the ball, final momentum for the ball equals mass times velocity, 1 kg, multiplied by 4 meters per second. Why not negative 4? Because remember, when it was down, it was negative 4 meters per second. When it was going up, it's 4 meters per second. And that equals 4 kg dot meters per second. As you can see, same as this guy here. Once we have the final and the initial, what can we do? We can go final minus initial, and that gives us the answer, which is over here. Perfect. Okay, let's go. What else can we do with momentum? Remember, I just mentioned that momentum can be calculated as a whole system. Like you want to calculate the momentum of the system, you calculate the momentum of each object in the system, and you can work out the net momentum. Just like those examples we've done with forces, when you've got like 5 newtons up, 5 newtons down, 3 newtons acting this way, 4 newtons acting this way, and 5 newtons acting this way, then you know the overall forces acting on the system is going to be 2 newtons acting this way. Why? You cancel this with this, you cancel this with the 7, what's left is a 2. So momentum is more or less in a similar situation. Physics repeats itself. It's lazy. So you calculate the momentum of this, you calculate the momentum of this, you calculate the momentum of this, you add them together, you make sure the velocity is the right sign. That's what you do. Cars hitting each other, one of them coming this way, the other one coming this way. How do you calculate the momentum of the system? Sometimes they'll ask you, I want the momentum of this object. Sometimes I want the momentum of this object. Sometimes they'll say, no, I want the momentum of the system. That's when you calculate the momentum of every single object and then you add it together. And that's what this is saying. The momentum of the system equals momentum of P1, P2, P3, P4. It doesn't matter how many objects you have. You calculate all the momentums. All of them. Okay, so what if I have an object coming this way and another object coming this way? Then the velocity here becomes positive and the velocity here becomes negative. What if I have an object coming this way? Oh, now you have to think about components. Break this one into components. That's all. What about this one? Break it into components. X and Y components. That's it. That's it. Okay. Right. We'll come, maybe we'll see an example like that. I think we will towards the end. But don't worry, it's very, very easy lesson. So here's an example. Duck, duck, goose. At a city park, a person throws some bread into a duck pond. Of course, ducks and geese love bread. 4 kilogram ducks and a 7.6 kilogram goose paddled rapidly towards the bread from opposite directions. As you can see, yummy, 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 yummy bread. So these ducks here are running towards the bread. Num, 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 num. If the ducks swim at 1.1 meters per second, okay, and the goose swims at 1.3 meters per second, find the magnitude and the direction of the total momentum of the 3 birds. It wants the total momentum. Hang on, hang on, hang on, hang on, hang on. Total momentum of the 3 birds. And now we're back to the pen. And I think I'll go with orange. I never use orange. So let me try orange. Step 1. Step 1. What do I do? Step 1, I'm going to write the total momentum of the system is equal to P1 plus P2 plus P3. This is going to be P1. Oh, why did I write P2? This is going to be P2 and this is going to be P3. Next, I'm going to make sure that I do the signs correctly. So does it tell me which one is positive? Because sometimes the question will tell you take right as positive, take left as positive, take east as positive, take south as whatever. You understand. It doesn't say. So it is my choice. I'm going to make this positive, which means I'm going to make this negative. Why? Because I just arbitrarily decided that this is going to be positive and this is going to be negative. It doesn't matter if you flip it. It doesn't matter. But I'm deciding that this is positive and this is negative. Since it's traveling that way and traveling this way is positive and traveling this way is negative. Okay, I'm switching colors. Sorry, orange doesn't work very well for me. How about this color? So now what do I do? Let's work out the momentums. The momentum of the goose, the big mama, is going to be P1, so that's going to be 7.6, because remember, momentum equals mass times velocity. So it's going to be 7.6 multiplied by 1.3 plus, what's the momentum of, this is step 2 now, total momentum, working out. The momentum of this guy, well, how much does he weigh? What's his mass? 4 kilograms. Remember, this is mass and this is velocity. So this time it's going to be 4 multiplied by negative 1.1. Well done for those of you that remembered. Well done, Senate. And Missouri, don't worry. Right. And now what do we do? And now it is 4 multiplied by negative 1.1. Okay. I wonder if Abdullah Shmamri has worked it out. 7.6 times 1.3 minus 4 times 1.1 minus 4 times 1. 1 point. How many significant figures are we working with? 2, 2, 2. Remember, you always take the least one, the smallest one. So it's 2 across the board. 1.1 kilograms, meters, kilograms, meters per second. Which way? It is going to be that way, to the right. How do I know? It's positive. It's positive. It's not negative. This one has a negative momentum. This one has a negative momentum. This one has a positive momentum. Overall, it was positive momentum, which means it's moving to the right. Inshallah, easy. Here's a follow-up. Should the speed of the goose be increased or decreased to make the total momentum of the 3 birds add up to 0? Verify your answer by calculating the required speeds. Of course, it should be decreased. Why? How do I know that? Well, because it was the overall, the speed was going that way. Okay, so it was in favor of the goose. So the goose had more momentum. The goose had more momentum. So in order for the goose to have less momentum, either it has to lose weight rapidly, go on a very strict diet, or it can slow down. And it says verify your answer with a calculation. Okay, so the total momentum on this side, the negative from the 2 ducks, has to equal the positive to make it 0. So they have to equal each other. Right now they don't equal each other. Well, how do we know? Because it's going 1.1 this way. We want it to be equal to each other. We want to work out this side first. So the 2 ducks have a momentum of 4 kilograms mass times velocity, which equals 4 kilograms multiplied by negative 1.1, which equals times 2, because there's 2 of them. Negative 4.4 times 2, negative 8.8. I want the goose to have a momentum of 8.8, but it doesn't. At the moment, it has a momentum of 1.3 times 7.6, which is close to 10. 1.3 times 7.6, 9.9. So what do I do? That is the momentum, and here mass times velocity. I know the goose has a mass of 7.6. I need to work out goose. I mean, I know there are male geese. Obviously, there are male geese, but we always think goose is a female. So I'm going to use her. We got to work out her velocity. I think Duerji agrees with me. Divided by 7.6. Therefore, I like using the three dots. Therefore, her velocity is going to be 1.2. 1.1579, but of course, two significant figures. So 1.2 meters per second. What was she traveling before? 1.3. So she just has to slow down a little bit, and then the momentum of the system will be zero. 1.2. Very good. Question 5 says, a car and a bicycle move towards each other, traveling in opposite directions. Each has a speed of 12 meters per second. So I'm just going to be lazy and I'm going to say car, 12 meters per second. And I've got a bicycle, and the bicycle, of course, is a lot smaller. And I'm just going to say B. But it's traveling at 12 meters per second too. This one has, so this is the velocity, and this is the velocity. I can, of course, choose that to be negative if I want to. And then the mass of the car is 1 to 50. The mass of the bicycle is 81.6 kg, and of course kg. What is the total momentum of the system, assuming that car moves in a positive direction? Oh, okay, so it does tell us the car moves in a positive direction. I just have to calculate P1 and P2 and just add them together. Very easy. So it's going to be 12 times 1 to 50, 15,000 kilograms meters per second. That's for the car. So, and then P for bike equals negative 12 multiplied by 81.6. Negative 979. I just add these two together. So it's 15, answer plus 15,000. I think we are working with three significant figures, four significant figures, three. So we got to work with three significant figures. The answer is, oops, what is that? Ah, that's the zoom function. Interesting. The answer is 14020.8. Actually, it was 140 and then 00 kilograms per meters per second. Okay. Why? Because the 2 here becomes a 0. It's not significant. Question 6. I'm going to have to just take some of this stuff off, if you don't mind, and move on. I hope some of you are attempting to do these before I do them. That's the way physics is done, guys. Okay, you have to actually try and do it yourself first. And, if you can't, then then you watch me do it, and then you do the next one in your own. But please don't just watch me do it. If you won't learn anything, remember it's the same as driving a car. You watch your parents drive a car every single day, or you're in a taxi or with the driver or whatever. You only learn how to drive a car once you take the steering wheel and you start driving. So it's the same here. You watch me do the problem and you think you're revising, you're not. You're wasting your time. Please, get your calculator out, start doing the problem. Get your notebook out, do the problem. Okay? Pause the video, do it, and then check with the workout that I do. Also, it's good practice to make sure that you do it in the four stages that we talked about: formula, workout, answer, units. Formula, workout, answer, units. Question 6 says a 1,200 kilogram car moves due north. Car moves due north at a velocity of 15 meters per second. An identical car moves due east. Ooh, interesting. Interesting. We have another car. Now, this is a remarkable question. I like this one. Moves east, also with the same velocity, 15 meters per second. What is the direction and the magnitude of the system's total momentum? The mass equals 1,200 kilograms, and this one has a mass of 1,200 kilograms. Easy. So the momentum for both of them is going to be exactly the same, except the direction. I'm going to take this off because I'm going to need it. I'm going to need this space over here. Sorry. Okay, let's have a look. The momentum for the first car is going to be 15 times 1200, which is 18,000 kilograms per meters per second. Guess what? It's exactly the same for the second one, so it's 18,000 kilograms per meters per second. Now that I have the momentum and I have these are vectors, remember? So I have a triangle. Oh, sorry, not quite right. They have to be more or less the same size. 18K, 18K. K just means kilo. Kilo means 1,000. I've mentioned this before. So kilo means 1,000. Kilo newtons, 1,000 newtons. Kilograms, 1,000 grams. Kiloliters, 1,000 liters. Kilobytes, 1,000 bytes. The word kilo does not mean like kilograms, but nowadays everyone says 4 kilo, they think means 4 kilograms, but kilo just means 1,000. You can even say I have 4 kilo dinars, for example, 4,000 dinars, but never mind. So 18K, 18K. So what we need to work out is the total momentum. The total momentum is going to be the hypotenuse. So a squared plus b squared equals c squared. We are trying to work out c. So c is going to equal the square root of a squared plus b squared. So it's going to be the square root of 18,000 squared plus 18,000 squared. 1,000 squared times 2. That's a big number. 6.48 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8. Square root of that, which equals, oof, oh, how many significant figures? 2. Okay. 2,500 kilograms meters per second. At 45 degrees north of east. Okay, let me just highlight the answer in case somebody gets a little confused. That's the answer. Okay, let's move on. Well, we are nearly finished actually, so short lesson. Let's look at the lesson check. Once again, I would encourage that you try and do these. So pause the video and then check the answers with me. 7.1 lesson check. Apply. How does momentum change if the mass of an object is doubled? It doubles. You double the mass, you double the momentum. How do I know? E equals mass times velocity. Let's give velocity any value, 1 meters per second, okay? So if we say an object has a mass of 2, it will have a momentum of 2. Let's double the mass as the question suggests. Let's double the mass. Let's make it 4. We keep the velocity the same. And suddenly it equals 4. So what happened to the momentum? It also doubled. Double the mass, double the momentum. Double the mass equals double z momentum. Right. Question 8 says, explain how is the direction of the momentum related to the direction of velocity? We already established that they are the same direction. Why? Because mass is a constant, it doesn't affect anything. Question 9 says, compare the speed of an object doubles. How does the change in the magnitude of the object's momentum compared to the change in its kinetic energy? Hmm. I'm wondering whether I should answer this question because obviously we didn't cover the unit on energy. Um, I'll answer it anyway. I just want you to know that I won't be asking you such questions because we haven't actually covered energy. So momentum equals mass times velocity, while kinetic energy equals a half mv squared. Um, if you double the object speed and momentum, it's going to double the momentum. So you double the object speed and momentum, you double the momentum. Why? Because we just figured it out before. So basically, if you keep the object mass anything, like let's say 1 kilogram, and the speed is 2, then the momentum will be 2. If you double the speed to 4, and you keep the mass the same, then the momentum will be 4. So you can see it doubles from 2 to 4. Not the case with kinetic energy, and not the case with kinetic energy. It quadruples. Why? Let's have a look. Let's take the same exact scenario, an object that is 1 kilogram. So here is the object, 1 kilogram. And the speed, we start with 2 meters per second, exactly the same scenario as we have here. What will be the kinetic energy? The kinetic energy will be half times m times v squared, which means half times 4, which means 2. And the unit for energy is joules. So far, so good. What happens if you double the velocity? So we went from 2 to 4. The mass is still the same, of course. 4 squared, oof, I can see some of you already figured it out. 4 squared is 16. Half of 16 equals 8. Look, it didn't double, it quadrupled. So that is the difference. In momentum, if you double the speed, you double the momentum. In kinetic energy, if you double the speed, you quadruple the kinetic energy. What does that actually mean? It means if a person is traveling in their car at 50 kilometers per hour and they crash, they are going to experience half the energy that somebody who is traveling at the same speed, sorry, double the speed and has the same mass. So if two identical cars, two identical drivers, same mass, one of them traveling at 50, the other one traveling at 100. The one traveling at 100 is going to experience 4 times the energy. 4 times. It's going to be, it's not just simply, oh, traveling twice the speed. They experienced twice the energy or twice the damage. No, no, no. 4 times the damage. 4 times the damage. Yes, really. 4 times. What's going to happen if they travel 4 times the speed? Can you guess? Can you guess? Not 4 times the damage. Yeah, 16 times the damage. Yeah. So if they are traveling at 200 kilometers per hour compared to 50 kilometers per hour. All right. Um, not our topic anyway. Sorry, it's just a little bit of a side note on energy. Question 10 says a system consisting of two particles is known to have zero total momentum. Does it follow the kinetic energy of system is zero as well? I don't like answering these questions. I don't want to confuse you. Questions 9 and 10, I will never answer these questions, ask you these questions in the test or anything like that because you didn't cover energy. Uh, but I will answer it briefly. Can the total momentum of a system be zero while the energy not be zero? Yes. How? Momentum can cancel each other. So if we have -2 here and +2 here, kilograms dot meters per second, and +2 kilograms dot meters per second, then they can cancel each other. But this particle has a lot of energy, and this particle has a lot of energy. Energy is a scalar quantity. Energy is like, you cannot, there's no negative energy. So the energy is double. The energy of the system is twice. The momentum is zero, but the energy of the system is double. So that's why you can have zero momentum and non-zero kinetic energy. Of course you can. Question 11. Calculate the momentum of an apple that moves with a speed of 2.7. Okay, it's finally time to draw. I like drawing apples. You gotta make sure you get the base as well, and the shine, and of course the stalk. It's not the best apple, but anyway. What is, oh, maybe you can put some streaks on it. And of course, different colored streaks and different colored red. It's a free art lesson as well, Doesn't have to just be. You can even draw the shadow of the apple. Okay, there you go. That's how you do that. And then you put the stalk. There you go. Beautiful apple. Where were we? What is the momentum? V equals m times v, which equals 0.16 multiplied by 2.7, and that equals, sorry, there's a limit to how much I use my brain. 0.432 kilograms dot meters per second. That is question 11. Question 12. A school bus has a mass of 18,200 kilograms. The bus moves at 12.5 meters per second. How fast must a 0.142 kilogram baseball move in order to have the same momentum? Interesting. So the school bus momentum, I'm not going to draw the school bus in a big detail, okay? Don't worry. Just, there you go, very brief. So the school bus has a momentum of 18,200 multiplied by 12.5 meters per second. 18,200 times 12.5, and that equals 2 million, no, 227,500. So we take this number and we divide it by the mass of the baseball, and we can find out how fast the baseball needs to be, because the baseball obviously is very, very, very small. So the mass of the baseball is 0.142 kilograms, and we are trying to work out the velocity in order to equal to 227. So divided by 0.142, it needs to be traveling at more than 1 million meters per second. So 1.6 million meters per second. That's how fast it needs to be. Question 13. I'm gonna rub off question 9 and 10. They're not relevant anyway. Question 13. A dog running with a speed of 1.9 meters per second has a momentum of 17 kilograms meters per second. What is the mass of the dog? Mass equals momentum over velocity. Do I have the momentum? Yes. Do I have the velocity? Yes. 17 divided by 1.9. About 8.8, 8.9 maybe. 17 divided by 1.9, 8.9 kg. And number 14. Number 14 says two carts move directly towards one another on an air track. Cart 1 has a mass of so and so and a speed of so and so. Cart 2 has a mass of so and so and a speed of so and so. What is the total momentum of the system, assuming the cart 1 moves in the positive direction? Excellent. Nice question. I'm not going to do that one. I'll let you do that one yourself. Um, just remember when you're doing the last one, make sure that the velocity has the right direction. Okay? I hope that wasn't too hard. Thank you very much. I'm going to end my video with something one of my students in grade 8 told me to say. Like, share, and see you على خير. Take care. مع السلامة.